All right, AP Calculus BC 2018 for response question number 3. We're going to go through that together. Okay, so 3A is a classic new equals old plus net change. It says if f of 1 equals 3, what is the value of f of negative 5? Where they're telling you that the derivative of f, which is g, is shown. So I know that f prime is equal to g. I'm looking at g. I have an old value of f. I want a new value of f. Okay, so what I'm going to do, okay, which is the way a lot of you guys are approaching this, is that I'm going to say that f of negative 5 is going to equal f of 1 plus, now the thing I want you to be really careful about is the way that you write this integral, okay? The lower values need to match. So this is a 1, okay? My lower bound is a 1, okay? This is a negative 5, then my upper bound is a negative 5, okay? And then what am I going to put inside the integral is going to be f prime dx. All right, now the next thing you need to notice is that this integral is backwards, that I'm supposed to go from 1 to negative 5. Well, that means that I'm really going to, instead of adding on that integral, I'm going to subtract the integral from negative 5 to positive 1. Okay, it's a different way of looking at it from what I've been encouraging, but it might be an easier way for you guys to see it. So just, you know, they're asking for f of negative 5, so f of negative 5 is f of 1 plus, and just make sure the lower bound, okay, that's why I did them both in red, the lower bound is 1, so I have f of 1 here and here, okay, and then my upper bound, which is outside, is my negative 5, and that matches my upper bound. Okay, and then just to recognize then that the interval is backwards on the integral, the interval of the bounds of the integral are backwards. So instead of going from 1 to negative 5, I'm going to make it from negative 5 to 1, and I'm going to negate the integral. So what does that mean? Well, it's the integral from negative 5 to positive 1. So we're talking about this area beneath the x-axis, and then I'm going to actually color code these a little bit to make this work a little simpler for this. And then I've got this area, and then I've got this area. Okay, there's no area between negative 1 and 0. Oh, they are different sized triangles. I apologize. Okay, I thought that maybe I was going to get off with some less work because they were triangles of equal area, but they're not. Okay, so I'm going to say that my f of negative 5 is equal to f of 1, which we're given is a 3, minus whatever I get here. So the blue part, this blue box here, is going to have a negative value because it's below the x-axis, and it goes from negative 5 to negative 2, so the base is 3, and the height is also 3. And then I'm going to also have a negative because it's below the x-axis. The area of the triangle is going to be 1/2. Base measures 1, height measures 3. And then my last, I'm going to make that a purple triangle. I'm going to be adding that, and it's going to be 1/2 base 1, height 2. So I should actually leave it like this, and let me just write it a little nicer because it looks like a total disaster right now. All right, just put it down here. Okay, and I would just leave it like that. If you do simplify it, you will get the value of 25/2, I believe. Please don't evaluate that. Set it up and walk away. Okay. All right, moving on to Part B. Part B asks for the integral from 1 to 6 of g of x dx. So the integral from 1 to 6 is this area plus this area. Okay, and some of that area can be found using geometry, and some of it has to be found using calculus. Okay, I just cleaned up my picture a little bit, but so I have a little bit of a square right in there. And the area of that square is base 2 times height 2, right? The base goes from 1 to 3, that's a base of 2. And then the green region, I need an integral to integrate that. So the very first thing is I need to name this function. It's a parabola that's been shifted right 4 units. Oh wait, they give it to me. Okay, so what am I going to do? I'm going to integrate that. Okay, so I'm going to take the integral from 3 to 6. Of g of x dx. Okay. And that integral I'm going to have to integrate by hand. So, right, this is the non-calculator portion. So for the first piece, I have 2 times 2, which is 4, and then I'm going to have the integral from 3 to 6 of 2 times the quantity x minus 4 squared dx. Now, some of you guys FOILed it out. I don't want to FOIL it out, so I'm going to just do a little u sub on it. I'm going to let u equal x minus 4. du is going to be a dx, and I'm going to have the integral of 2 times u squared and just a du. Okay, my bounds, I'm going to change them. I'm going to go from 3 minus 4, which is negative 1, to 6 minus 4, which is 2. I'm also going to carry down the 4 on here. So I have 4 plus, right, the same 4 from before. Okay, so I'm going to have 4 plus, and then this integral, I'm going to now integrate, so I have the antiderivative of 2u squared is 2u cubed over 3, and I'm supposed to go from negative 1 to 2. So I'm going to, right, that's just for this piece. So I'm going to keep that 4, okay, and then I'm going to add on 2 times 2 cubed over 3 minus 2 times negative 1 cubed over 3, and I'm going to leave my answer like that because I can. Please do not simplify this. I said if you do simplify it, you get a 4 plus a 6, which is a 10. But please don't simplify it. It's a waste of your time. Okay, moving along. Okay, I know a lot of you guys had questions on part C, on what intervals, if any, is the graph of, oh wait, not C, it was D that a lot of you guys had questions on. Let's deal with C. We want F to be increasing and concave up and give a reason for your answer. Okay, so let's go by the facts there. Okay, so this should be old hat at this point, that F is increasing when F prime is positive. I'm noting in that same statement that F prime is equal to G. Okay, so F is increasing when F prime is positive. F is concave up when F double prime is positive. I'm also in that same statement now saying, well, if F prime is G, then F double prime is equal to G prime. Okay, I'm making those connections. You need to make those connections for AP. Okay, now tie it back to what we're looking at. What are we looking at? We're looking at the graph of G. So I want G to be increasing. That's going to be when G is in, okay, so now, sorry. G is increasing, right? G is increasing on this interval here. Okay, and also this interval, and also this interval. And I need G to be positive. Okay, so of those, G is positive on this interval and this interval. So our answer is, for C, it's from 0 to 1. And again, from 4 to 6. Okay, all right. So the issue that a lot of you guys had in Part D was whether or not you stuck to the true definition of a point of inflection for F. Okay, so let's look at the true definition of what a point of inflection for F is. Okay, and that's that F has a point of inflection when F double prime changes signs. This graph that we're looking at is the graph of F prime. Okay, so in order for F double prime to change signs, G prime has to change signs. That means that G has to change direction. Okay, and what I want you guys to understand while we're talking about this is that these places where F prime, which is G, has slopes of 0, the slope, if G has a slope of 0, G has a slope of 0, that means that this has a value of 0 over here. That means the second derivative is 0. That's not concave up or concave down. So there's no concavity on these intervals. Okay? Now, if this relationship is true, where F double prime is equal to G, I don't think that came out right, where F double prime is equal to G prime, I didn't write it right and I didn't say it right, then I need F double prime to change signs, I need G prime to change signs, I need G to change direction, and the only place that G actually changes direction is at x equals 4, where G goes from decreasing to increasing. Okay? Okay. So I need the derivative to change direction for F to have a point of inflection. So it's only happening at x equals 4. Another connection that you guys can make from when we back to like graphing, we were looking at derivatives and then graphing the functions. When a derivative has a constant value like it does here, That means the slope of the original function is constant. When you have a constant slope, you have a linear segment. Linear segments don't have concavity. So this initial bit is a graph with a slope of -3. Okay, and then I have a graph that is decreasing concave up, and my interval is wrong, and then it switches, but these linear segments are constant values to the derivative, which means that the function has a constant slope, which means that the function is linear, which means the concavity doesn't exist. So you can't talk about a change in concavity when you go from no concavity to concavity. Okay, so that's why x equals 4 is the only true point of inflection, because you're changing specifically from concave down to concave up. Okay, all right.